So for the type of reactor, we have chosen the conversion reactor. The conversion reactor is a CSTR that specializes in conversion reactions. It can only work with reaction sets that include that reaction type. The reason we choose this reactor is to control the conversion rate. A conversion reactor constantly adds reactant and withdraws the result. To guarantee homogeneous chemical composition and temperature, enough agitation is necessary. The operating conditions are as follow. The CSTR reactor's temperature is set at 60 degrees Celsius and also 400 kPa pressure. According to study, the time it takes for the transesterification reaction to complete is shorter when compared to temperature lower than 60 degrees Celsius. The catalyst which was used is potassium hydroxide. The advantages of using potassium hydroxide is that the reaction will cause low and also high activity and safe for the environment. The conversion rate for the first CSTR is 20% and for the second CSTR is 60% to achieve 80% conversion.
Description of the reactor. So based on the reaction used in biodiesel production, tripalmitin, methanol, palmitic acid and glycerol are among the 4 components of the input solution that enters the separation unit. Our separation process contains a total of 2 separation units to totally separate the biodiesel from the feed that we are manufacturing in order to manufacture pure biodiesel. The first separation unit separates glycerol from triglycerides, methanol and biodiesel using a ceramic membrane. And the last separation is process methanol separation, which is after the separation of the glycerol, the methyl ester passed through a methanol stripper, which is the following film evaporator, before entering a neutralization step and water washing. Next is to maximize the selectivity and yield of the biodiesel. When it comes to speeding up reflexes, adding heat is always a good idea. Temperature increases the rate at which biodiesel is created in biodiesel manufacturing. Besides adding heat, basic catalysts such as sodium or potassium hydroxide are also effective at speeding up the biodiesel production process. Next is by adding the alcohol for more optimal production. However, if there is too much alcohol, separating the biodiesel from the glycerol might be problematic since the glycerol becomes more soluble in the biodiesel. The type of alcohol used in biodiesel manufacturing can also have an impact on its overall efficiency. For the volume of the reactor, we use the formula Fn naught times by X, which is the conversion, and divide by the negative Ra. For CSTR1, we got the volume of 0.0452 meter cube, and for CSTR2, the volume is 2.338 meter cube.
Next, we will move on to the process modeling simulation. In this case study, the conversion of triglyceride into methyl palmitate in a transesterification process is being studied. The simulation was carried out using symmetry, and the unit operations includes a mixer and 2 CSTRs connected in series. The objectives in this study is to simulate the steady-state reaction process of transesterification and validate the simulation by comparing it with manual calculations, provide the deviation error between simulation and manual calculation, and perform sensitivity analysis by altering several parameters. Here we have the results of our simulation using the same volume and reactor parameters that have been specified in the reaction engineering part. The deviation error from the simulation and calculated values were very minimal. The total molar flow from CSTR1 has a deviation error of 1.457%, while from the CSTR2 has a deviation error of 3.44%. Hence, it can be deduced that the deviation error may originate from human errors from the manual calculation.
So in this part, I'm going to discuss how the process is feasible and changing heat flow and temperature and heat composition. According to above graph, you can identify values and that's proportional between both temperature and heat and flow to the product composition, while increasing the temperature or the heat and we got lower composition of the product. And this only applicable for the first CSTR reactor, were no change on the product composition in the second CSTR reactor. Where changing the reactant composition should be within a specific ratio, where the max ratio is 0.2 for the triglyceride to 0.8 of alcohol.
So for sufficient assessment, we will start with overall behavior and then we will move on to the description of potential units and the calculation of specification units. This is the overall behavior where we will come from CSTR and then we will go to pump and valve and we will go into perception unit which is membrane unit and then we will go through evaporator unit and then we will go to neutralization and washing unit before going to storage tank. So this is the description and calculation of the separation unit. We will assume that the membrane is ceramic membrane with ultra filtration, as we will assume that the filtration surface area will be 0.25 square. Only glycerol will be removed. In this process, chlorine is low at the peak side, so the C1 equals to C1i plus the flow of steam to the peak. The retention of glycerol is 99.4%. The thickness and length is 30 picometer. The visibility of glycerol is 8.5 times 10 power of 20 and it is calculated at the temperature of 50 degrees Celsius. And lastly, the permanence of the ceramic membrane is 23 meters per second and force size of 0.02. Calculation, first we calculate the value of NA equals to F over A and NA equals to 4.689 times 10 power of 24 kilomole per meter square second. And then we calculate the concentration of the second one, which will be C2 equals to 0.0419 kilomole per meter cube. Then we calculate the value of K5 PM times L over the APU. The current will be 109.9. Next, we will calculate the value of KC2 and we get KC2 to be 6176 times 10 power of 24 meter per second. And after that, we will calculate C2I value using NA equals to KC2 in bracket C1 and C2. And C2I equals to 0.6948 kilomole per meter. After that, we will input C2IS using K prime equals to C2IS which is C2I and C2IS will be 796.36 kilomole per meter. After this, we will input them in a table of components and concentration. For the second separation unit, we will use flash evaporator and we will assume that the pressure drop is not too large so we can control the flow rate. We'll assume that 100% of metal will be recovered and that the unit will be very well insulated so there will be no heat loss to sound. To start the calculation, we first will find the value of L, where F equals to L plus E and L will be 1.887 kilomole per hour, and then we will find SIL, where it will be 0.67. Next, we will find the value of S using formula F plus SL equals to L HL plus EHV. The value of S will be 0.9894 steam per hour, and then we will find the energy needed using Q equals to SL and Q equals to 0.061. And then we will have to find the flow rate of the working product, where we will get the value to be 342.47 kg per hour. And from that, we can calculate the mass flow rate of the product, where the mass flow rate will be 3000 tons per production